Hello and welcome to the presentation of a paper named Methodology for the Selection of an Optimal Location of Remote Tower Center, done by Tetiana Shmelova, Svitlana Kredentsar, and Maksym Yastrub. My name is Maksym, and I'll be the one presenting it today. We will, of course, start with the actuality of the work. As you may know, a small amount of flights in small regional airports is a common issue for many countries around the world. Most of the small airports struggle to break even, however, at the same time, provide necessary points of access to remote locations and contribute to the local economic development. In Ukraine, most of the airport air traffic is concentrated in just a few major airports such as Kyiv, Boryspil, Zhytomyr, Odessa, Lviv, Kharkiv, while 67% of annual passenger flow and 44% of instrument flight rules flights are handled just by one airport, Kyiv-Boryspil Airport, thus leaving just a small fraction of airport traffic to other regional airports of Ukraine, which limits their developments and keep air navigation services costs high. One of the ways to reduce air navigation service costs and attract more flights to regional airports is an implementation of remote tower concept. The core of the concept is provision of air traffic services from a remote location to one or multiple airports at the same time. The provision of remote air traffic control services requires a continuous exchange of information between the air infrastructure at the airport site and a remote tower center. Usually, the equipment that you would find that is necessary for the provision of remote tower services includes high-resolution video cameras, pan-tilt zoom cameras, video signal encoding equipment, high-resolution displays to provide the out-of-the-window view for air traffic controllers, navigation and light systems, surveillance, and other types of sensors. Because of that, we know that the requirements for the network connection is very high to ensure safe and orderly provision of remote air traffic control services. And because of the very high requirements for the network connectivity, we also need to have a look into the network performance that would support the implementation of remote tower concept. One of the factors that have a high impact on network performance is latency in time. The network latency, or it might be called data transmission delay, can be defined as an expression of time needed for a data packet or message to travel from one end of the network to another. Ideally, the latency should be as close to zero as possible. And the value of the latency depends on three main components. Speed of light propagation delay, that depends on the medium through which the light travels, amount of time to transmit a unit of data, that depends on the network bandwidth and the size of the data, and the queuing related delays that can depend on the software or the hardware that is used to transmit the data. In this research, we are focusing on the reduction of the propagation delay for the exchange of information to ensure that the latency of the network is as low as possible. The propagation delay can be determined as a ratio between distance over which the data has to travel and the speed of the propagation. Since the speed of propagation is relatively constant and equals to speed of light in the given medium, the only variable that we can change is the distance. In case of the remote tower concept, this is the distance between remote tower center and airports to which it provides remote tower services. The optimal location for remote tower center will contribute to the reliability of the air traffic control systems by balancing safety and economic efficiency brought by the implementation of the given concept. We know that the regional airports of Ukraine are scattered throughout the territory of the country, and because of the long distances between the airports and the potential locations of remote tower centers, that could lead to high values of data propagation delays, which could compromise safety and delay the provision of air traffic services to the airports. The most optimal way to ensure the minimal distance between airport sites and remote tower centers would be grouping airports that are located nearby into segments and deploying remote tower centers per segment to serve airports within it. That's why we divided the task of finding an optimal location for remote tower center into separate steps. Step 1 would be to group the airports into segments, for example, done in accordance with the map of Ukraine and the location of airports, as it has been proposed in the previous slide. In the step 2, I would calculate the coordinates of remote tower centers to minimize the distance between remote tower center and airports within the segment. And step 3, to refine the coordinates based on other parameters, for example, density of traffic, availability of resources, and so on. During this research, we are going to focus on step 1 and step 2. The step 3 is going to be tackled in the follow-up studies. We'll start with the step 1, grouping of airports in segments. In short, we'll take an airport and would look into 3 airports around it and take only 3 ones that have the smaller distance between that airport. We'll create a list and calculate the number of appearances of the airports in that list. Based on that, we would be able to create segments of airports and split the regional airports of Ukraine into segments. Based on that information, we can go in further and calculate the initial coordinates of the remote tower center within the specific segment using the following formulas. These coordinates are used later on as a starting point for the method of gradient descent to refine the coordinates. As I already said, using the method of gradient descent, we are refining the coordinates of the remote tower center, trying to minimize the functional described in the slide to make sure that the distance between the remote tower center and airports within the segment is minimal. This is just a further explanation of the method of gradient descent and how we determine whether we are ready to stop our calculation or we have to continue and find the new value of the functional. At the last step of refining the coordinates, we use a method of golden section search. In this case, we try to find an optimal point, an optimal location within a given interval, and based on the values that are described on the slide, we try to understand if we can continue the process and look for a new value, or we have to stop and we have reached the value that we are looking for. As you could see, step 1 and 2, purely mathematical, of the methodology provides us with a set of coordinates of an optimal location of the remote tower center just from the point of view of minimization of distances between airports within one segment. But we know that this is not the only factor that influences the decision for the selection of the location. We could name such factors as density of the traffic of airports within a segment, availability of resources at certain airports, availability of human resources, for example, air traffic controllers at airports, and so on. And we need to take those factors into account as well. That is the step 3 of the methodology that has not been developed within this paper. We have taken this methodology as described in the previous slide, and we have implemented it as a computer program that takes a set of airports of Ukraine as an input and calculates the number of segments, performs allocation of airports to these segments, calculates and refines coordinates of the remote tower center per each segment. We've taken the set of airports just as an example, and of course it can be changed depending on the variation of traffic or any other parameters. The received data and the analysis of above-mentioned factors can be used later on to support the decision-making process for the selection of an optimal location of the remote tower center. On the picture you can see the outcomes of the execution of the program, where you can see that with the blue dots the initial coordinates of the remote tower center, and with the green one the refined one. In some cases it was enough the initial coordinates and the refinement process didn't bring any new values. In some cases we could see some shift in terms of minimization of the distance. So this research focused just on one component of the latency, the propagation delay for the exchange of data, to ensure that we have the latency of the network as low as possible. To that, we tried to minimize the distance between airports and remote tower centers and select the optimal location for a remote tower center. And for that, we used the method of gradient descent, and we have adapted, of course, it to be able to use in the context of regional airports of Ukraine. The received method provides a set of coordinates of optimal locations of remote centers from a point of view of minimization of distance between airports within one segment. However, we do understand that this is not the only factor that influences the decision or the selection of the location of the remote tower center. Other factors such as density of traffic, availability of resources, and so on should be also considered. That's why we are planning to launch a separate follow-up studies to define such factors and investigate their influence on the decision of the selection of the optimal location. And you can have a look at our ideas for the future research. It is proposed to find the optimal location of the remote tower center depending on the influence of several factors: location of the airport, current intensity of air traffic, workload of nearby airports, and so on and so on. It is necessary to perform an additional study and investigate other factors that could have impact on the selection of the optimal location of the remote tower center, and to enrich the current methodology with the defined factors. Once the methodology is defined completely, it can be used also for other countries to select optimal locations for the remote tower centers. Thank you for your attention, and bye.